So you have the test there. The tests are graded out of the top score, which is, the highlighter is not the best choice. So the grade out of 87. So your grade will be, like let's say that you got 60. It's 60 out of 87. And of course, you can calculate the percentage based on that. 60 out of 87 is probably around 70%. Okay, the last problem on the test, the calculus one, I just want to go over it. The calculus one, we had a window, a little plexiglass window, in not a swimming pool, an aquarium tank. And the water level is up here. I think it's depth, so I went downward for my y direction. And y top was 2.5 meters. And y bottom is 12.5 meters. And then we're asked to find the net force on the window due to the air on the outside. So the air on the outside can have a force outside is equal to atmospheric pressure times the area. And the force on the inside is going to be changing with depth because the pressure is changing. And so on some little region here, I'm going to have dF is equal to pressure inside times dA. And then I have to integrate that over the height. So then I know that pressure inside is equal to pressure atmosphere plus the density of my water times G times the depth. And my dA, since this, if you look at a side view of the window, it has a width equals 20.0 meters. And of course, it has a height of 10.0 meters. And so some little piece dA, I'm going to go like this. Here's my little piece dA. dA is equal to the width multiplied by the height of that little slit dy. Why did I do that? Because then it makes it a one-dimensional integral. Just a single integral, the kind of integral that all of you are comfortable with. I mean, I could have done a double integral. It would have been very simple, but going to the simplest of doing the single integral. So now I just have to put everything together with my limits. And I'll put E in there. Force in is equal to the integral of d force in, which is equal to the integral of pressure in dA.
In is representing initial? Infinitesimal?
What was that?
In is representing inside?
The pressure is a function of depth. It's this function right here.
Okay. Well,
and the infinitesimal is the dA.
But what is the IN?
Oh, in is inside. Okay. I misunderstood the question. So substituting in, I have an integral from my starting depth of 2.5 meters to my ending depth of 12.5 meters of pressure atmosphere plus rho gy and then w dy. So this is the dA right there, and this is the pressure in. And so then integrating that, I'm just going to put W at, I'll be a little more specific. P atmosphere W integral 2.5 meters to 12.5 meters dy plus rho G W integral 2.5 meters to 12.5 meters y dy. So I just multiplied through, right, the thing that's in parentheses, and separate it to two integrals. This first one is very simple. Right, that's what you get for the first integral. And then for the second integral, integral of y dy is y squared over 2. Now, I'm going to stop the calculation at this point because this here will be a number that you can calculate, and I don't feel like doing the actual calculation here in class time. For the force net, that's going to be equal to the force in minus force out, right? Because they're going opposite directions in my picture. So that's going to be equal to pressure atmosphere times 200 meters squared minus the stuff in that box. And then I have to subtract the force out, which is pressure atmosphere times the area. The area is 10 times 20 or 200 meters squared. And so those two leading terms subtract out, and my entire answer with the correct sign instead of the incorrect sign, that's a plus sign, is the thing that's in this box. So that was my method. Now, what was the concept here? The concept was that the pressure puts a force on the surface of, force is equal to pressure times area. Since the pressure is changing with depth, I have to change that to dF is equal to pressure dA and integrate over the depth because the pressure changes with depth. Okay, any questions about that problem? Because that was a toughie for you guys.
Yeah, I think I figured out what I did wrong. Multiple things.
Figured out how to do multiple things. All right, so we're going to work with the Maxwell-Boltzmann distribution. Here's the Maxwell-Boltzmann distribution right here. Now, this distribution is a probability distribution. That is, it's telling us about the probability of finding a particle with speed v to v plus dv. It's actually the probability within a range. So if you want the probability of having speed between v and v plus dv, that's equal to this function times dv. So that's why it's actually, in quantum we'd call this a probability density. Now you might ask, why? Why do I have to put the dv there to get the probability? What do you suppose the probability of having a particle with an exact speed is? 0. It's 0 to have an exact speed, right? That's an infinite number of decimal places. The probability of having that exact infinite number of decimal places is 0. Well, vanishingly small. And so what we have is a probability density, and then we put an infinitesimal width, but now we have a range. Probability of being in this range then becomes more manageable. So how are we going to use this? Well, let's look at the things here. Find what is the probability of being at rest if you just look at this function? If v is equal to 0, what do you get for that function? Inside the box.
0.
There's the two places v occurs. So if v is 0, you're going to have 0 e to the 0. E to the 0 is 1. So 0 times 1, 0. What about if speed is infinite? Notice that there is a minus sign here. If speed is infinite, yeah, it changes things. Speed is infinite, what do you have? You have infinity because v squared is infinity, right? Multiplied by e to the minus infinity. What's e to the minus infinity? 0. Now, which blows up faster, something that is an exponential or something that is a polynomial? Exponential. So we have an infinity times a 0. L'Hopital's rule would, of course, be the way you would evaluate this. But in physics, we often just have orders of infinity. Which is a bigger order of infinity? Exponential is a bigger order of infinity. So the going to 0 exponential is going to 0 faster than v squared is going to infinity, and so it's 0. So the probability of having a particle with 0 speed is 0. The probability of having a particle with infinite speed is 0, which is good. Now I have to point out one more thing. Our understanding of nature tells us that nothing can have a speed exceeding the speed of light in vacuum. This here would not say 0 if you put, for the speed, 299792458 meters per second. That's a problem. So this is the non-relativistic version of the equation. If you're at a super high temperature, you might have to shift over to the relativistic equation, because this says particles could be going faster than the speed of light, and that's not possible. So just pointing out that this is the simplified version, the one that works for classical physics, but not when you relativistic speeds means 1/10 the speed of light or faster. So if you have a high enough temperature that it gives you particles going that fast with some reasonable probability, it's wrong. You have to change to the relativistic one. And you know what? Offhand, I don't know what it even is. Question?
I was just wondering, why do we do it this way?
We do it this way because it works for standard temperatures that we encounter in our daily lives.
Okay, so for standard temperatures, the particle can never be going faster than this.
This equation is going to give us vanishingly small probability of having anything at that speed.
Okay.
And so that means that the difference between reality and this equation is vanishingly small. But if you have a high temperature, this equation doesn't give you that, and thus you can't use it. You should take off your backpack. I'm just thinking that can't be comfortable by the end of the class. Okay, so we've noticed those probabilities. Now, because it's 0 at both extremes, that means there is a most probable speed. The most probable speed is, if you plot it out, where it's at its peak, right? And so the first thing I want to do is find that most probable speed. How would you find the most probable speed? You do what? Okay, you find the max in the graph. And how do you find the max? We have a mathematical way of finding the max. We set the derivative equal to 0 and find the speed that makes that true. So we can find the most probable speed by taking the derivative of this function, setting it equal to 0. So the first thing I'm going to do is find the most probable speed, which here I wrote most likely speed. So to do that, first, we're going to take this function. Oh, look, this here is calculus stuff we're going to have to use for integrals. But since I said derivative, we don't have to use it right now. So here is the function written out in all of its glory. And here's the function written out in a very abbreviated form. I like the abbreviated form because it is less writing. Now keep in mind there is temperature associated with the capital B and associated with the lowercase a. So there will be temperature in there, but I'm not taking derivatives with respect to temperature, so it's not a problem to me. So finding the most probable speed, we said, is take the derivative of f of v with respect to v, evaluate that at v probable, and set it equal to 0. I say evaluate at v probable because that's what we're finding if we set it equal to 0. Right? If you set it equal to 0, you get only one speed. Well, in this case, you'll get 3 speeds. But you get a finite number of speeds, and those speeds are all the speeds where you're at a maximum or minimum. And so it's not just speed, it's a special one. So let's do the work. Who can tell me what the derivative of this form of the equation is with respect to v? What rule do I have to use? Product rule. So the product rule, let's call the first part BV, the second part e to the minus AV squared. So what's the rule for the product rule?
A plus B, A plus derivative A times the derivative B plus the derivative A times B.
Okay, A times derivative of B, so let's go, the A would be BV squared, times the derivative of B, derivative of e to the minus AV squared.
E to the minus AB squared times 2B.
Okay, we have to bring down the derivative of the exponent. What's the derivative of minus AV squared? Minus 2AV. So I have to bring down minus 2AV, and then I have just the exponential again. So there's my first term. Then my second term is going to be the derivative of the first. What's the derivative of BV squared with respect to V?
2B.
Yeah. 2BV. And then I just have the second function. Now for all of these, it's V probable now, right? It's not just for any V because I'm setting it equal to 0. Well, I already have equals 0 now, don't I? Now I am going to factor out what I can to rewrite this simpler. 0 equals BV probable, because they all have a BV probable, times e to the minus AV probable squared, because they all have that, times V probable plus minus V probable plus 2. Did I do that right?
There's an A.
No, I did not. There's a 2 in both of them, so I should have factored the 2 out up here because it's in everything. And so I have a minus A V probable, and then plus B. I factored, so
Yeah.
let me color code things. B 1/2 of this one, and the 2's are in the first one. And then in the second one, oops, stop that. So in the second one, I have this and this. And so in the third one, I have the other one of these. Oh, wait a minute. There should be a square here because there were 2 of them remaining. I could have made my life easier doing it this way.
What we're saying is you factored out that V.
I factored out that V probable for the first one, and then this V probable squared goes in the black one.
B.
Oh, the B?
B.
B is in bedroom.
And the second part of the addition term, there's an B1 there. In the bottom, I mean. It's third parentheses.
Yes, I see. It's good to have you straighten out my errors. Because yes, that B should have been there. So that's just going to be a 1 then. Because the VP, there's the 2B VP, that's all the first term. Okay, so there we should have it straight. Do we agree that's straight? One more thing here. The minus sign right there is in the black. So that's equal to 0. How many things do I have in parentheses? 3. That means you're going to have 3 different things to evaluate to what gives me 0. So let's take the first one. 2b VP equals 0. What value is VP? Okay, that's clearly not our maximum. That was a minimum. Take the second one. What speed makes that true?
That'll depend on,
Now, VP can only be a positive number, so there's only one answer.
but that'll depend on
The temperature is,
the temperature.
let us presume, a finite temperature. If it's a finite temperature, then A is not 0. Hence, what is VP going to have to be to make this entire thing 0? E to the minus infinity approaches 0.
And so,
So this is VP approaches infinity. Right? You can't equal infinity anyway because of what we just said, approaches. So we have the two that were already named up here. Okay, up here. We have those two from our first two terms. And so then the final one comes from the one in black. Let me fix my color coding some more. This should have been in red. And now we go to black. And we have therefore VP is equal to what?
square root of 1 over A.
So square root 1 over A, what is A equal to? A is equal to M over 2KT. So that's the only one that was new to us. The only one that actually is beneficial to us, that's the most probable speed. So that was really not that bad. Just take a derivative, find, set VP equals 0 and find, or VP equals 0, set the derivative equals 0 and solve for VP. We did have to be a little bit careful. We have 3 answers. We have to know which one we care about. In some cases, of course, you might have had more than one you cared about. Now, the total probability. The total probability is important. This is the probability distribution. So if I have one particle and I check what speed, what's the probability of this speed, what's the probability of this speed, and so on. If I add all of those up, probability for each speed, what should I get? Let's put it a different way. You take a test. You get 1. You take a test and, what's the probability of getting 1%, what's the probability of 2%. You add up all of those probabilities, in the end it's 1, because you know what? You do have a score. And you only have 1 score. Right? You don't have 2 scores, so it should be 1. So this is a rule. It's a rule that we call normalization. When we get to quantum mechanics, which is next semester, we will apply normalization, which is that the total probability, remember, f of v dv was the probability of being within a range of v to v plus dv. And we do our limits from 0 to infinity because even though we know that we're in fact limited to the speed of light, this equation is written for going up to infinite speed. So we do this, and that has to equal 1. If it doesn't, we have a problem. And so, well, that shouldn't be hard. We just do this integral. And we look at this and we squint and we get unhappy and we get angry. Because it's an integral of v squared e to the minus av squared. That's not a simple thing to do. And what we are not doing here is reinventing the wheel. We are not going to go and derive how to do this integral. That's why I gave you the handout. So if you look at that handout, we have the Maxwell-Boltzmann integrals, which are actually same as Gaussian integrals. We have our general form of I sub n is equal to the integral from 0 to infinity, those are the limits we're using, x raised to the n, e to the minus ax squared. Well, what is n for the case that I'm looking at right now? For this right here, it's v raised to the 2, so n is 2. So the answer to this is going to be b multiplied by I2, whatever I2 is. Well, how do I know what I2 is? I look at this table and it says that I2 is going to be 2 minus 1 over 2a times I0. And here's I0. So I2 is equal to that. Can I write that in a simpler fashion? I like to put all my numbers inside of the square root, so that would be putting all the numbers in the square root. So square root of pi over 16a cubed now, what is b? I have b written multiple ways here. And so I'm going to use the final one there, even though the final one, you might recognize it would have been easier to not put it in this form. Bring the 4a in. And what do we have? 1. We do that as a sanity check to make sure that our function is not violating a fundamental principle that you have to have the probability of the particle existing as 1. So, dodged a bullet.
What we're doing here then is, if we're looking for I2, we just say it's got to be, we take this general form that's in the bottom of the box.
Yes.
At n minus 1, so that'd be 2 minus 1 over 2a times I n minus 2, so that'd be I0. I0 is given for us up there.
Yep. So the I1 and the I0 are calculated for us, and then we're going to just go through and calculate any I beyond
and so
1,
if
0,
we
1.
needed to get like an I16, we'd have to go like I16, then put an I times I14, do that one.
Yeah.
Down.
Recursive.
So we get to 1 or 0.
Yeah. Which, of course, you would hate unless you had to find all of them up to 16, and then you're like, well, I've already found 14, so.
Right.
Now, at this point, let me mention on your next exam, which is 2 weeks from today, your problem will be from today's lecture. It will be something associated with what we're doing today. So we found the most probable. We have now found the total probability. And now we're going to go through a couple more variations. Find the average speed. So the average speed, how do you find the average? On a test, you have 3 people that got 80%, 7 that got 85, 10 that got 90. How do you find the average score? Okay, you add them all up and divide by the total number of people who took them. Or an equivalent way. What?
Nothing. That was not.
An equivalent way is to say, well, what was the probability of getting a score of 90? The probability is the number of people who got 90, 10 in my example, divided by the total number of people who took it, which I honestly threw out all the numbers, but I think it was around 20. So you say, okay, 10 over 20 is my probability. 10 over 20 is 1/2. And then I would take the probability of each score times the score and add all of those up. Well, that's how we're going to do it here. That's how we do it in quantum physics. Everything we're doing here is the same type of thing that we do in quantum physics. So it's kind of like preparing you for quantum, so when we get there, you're like, oh, I've already done something like this. I guess I spelled that wrong every time since I copied and pasted it over and over and over. Sorry. So what we're going to do is say the average speed, remember those things mean average, and once again that comes from quantum physics notation, is equal to the integral. Now remember my probability was f of v dv. That probability multiplied by the actual value. And so I'm going to do my calculation, but now it's going to be the integral of bv squared e to the minus av squared times v dv. I just changed the order of the last two because I like to have dv last. But of course, v squared times v is v cubed. So that's equal to b integral from 0 to infinity of v cubed e to the minus a v squared dv. What does, I get a bright idea and then I forget to enact it. What does this thing in purple equal? Keep in mind that's a 3 there.
3 minus 1.
Okay, you're going beyond what I was hoping to see. I was hoping to just say I subscript 3. So now we do what Alex just said. We look and we say, okay, that's equal to b times 3 minus 1 over 2a square root, it's that times I1, right? And since I1 is just 1 over 2a, 2 minus 1 turns out to be 2. We have that.
We're not even doing integrals at this point.
Well, we aren't doing the integrals because they're hard.
Yeah, we're skipping the integral because it's been done a million times.
Yes, it's been done many times, and we're not, like I said, we're not reinventing the wheel. If you read through this, it actually goes, usually I go through the math, but I decided I wanted to actually get to how we do stuff instead of going through the math, the explanation. But it shows how you get those integrals. And there's a non-trivial step right about here. Okay, so that's b over 2a squared. So now let's look at our different options for b. And again, the one that's probably going to be the easiest for me is going to be to use the lowest one, the 4a square root a over pi times 1 over 2a squared. Multiply those together and it's equal to 4 over 2 is 2. A over a squared is 1 over a. So it's square root of 4 over a pi. And then I plug in what a is. I have this on every one, so I won't forget a is m over 2kt. So that's square root of 4 over pi times 2kt over m. And so there is our equation for the average speed. which I believe I did right. I don't actually have the equation shown here, but I do have, oh, crud. I copied and pasted this from here on, and so I didn't put the actual right values here because I copied and pasted. I forgot. Oops. Yeah. So we now have calculated what the average speed is. The next one, the RMS speed. What does RMS mean? Root mean squared. So the first thing we have to do is find the mean of the squared speed, and then we're going to square root it. So we start with, what should I have for my integral? What was the general method to find an average? Probability. So in this case, our probability was f of v dv. There's our probability. Wait, say that? Times, I'll put it up front, times v squared, because we're finding the average of v squared. And then what did we do? We have the probability times the value. Not divided. Remember, the probability already has the division of like the number total. But this is just one value. We need to check all the values, right? So we need to add them all up. Mathematically, if it's continuous, that means integrate 0 to infinity over all possible speeds. That's it. Now I need to put in what f of v is. So that's equal to bring out the b, combine the two v's, and that's equal to b times what? I, which I? Not 0. Not 1. Oh, sorry. It's going to be 4 because it's the exponent associated with the variable of integral. So since it's v to the 4th, it's I4. So it's b I4. And so now I look at my table, and my I4 is going to be 4 minus 1 over 2a times I2. Okay, here you have I0, I1, and IN for any possible n. And so when I had I subscript n minus 2, I just wrote 2 here. Now, I'm going to do something you might consider cheating, but it makes my life happier. We started with the normalization, that is, making sure the integral overall space was 1. And when we did that, we got bi2. So we had 1 equals bi2. I'm not going to substitute in I2. I'm going to say right here, wait, I know that b times I2 is equal to 1 from my previous work. Because I just did it, I don't have to do it again. If I hadn't just done it, I would have to do it again. So that means my answer here is just 3 over 2a. Well, since b times I2 is 1, this is 3 over 2a times bi2, but bi2 is just 1. That was the result that we found right here. There's equal to 1, bi2. So 4 minus 1 is 3
Yeah.
over 2a.
Okay.
So this here is just equal to 1. So I have the average of the speed squared is equal to 3 over 2a. And so the RMS speed, how do I get the RMS speed again? Square root that. Square root both sides. I have VRMS is equal to the square root of 3 over 2a. And then I have to look at what a is, and a is m over 2kt. Notice 2 over 2 cancels. So there we found the VRMS is equal to square root 3kt over m. That agrees with what we found with the kinetic theory of gases. Once again, that's kind of important. If you get a different answer depending on which way you approach the problem, you know what you've done? You've made a mistake. Something would have to be wrong. And so the fact that we get the same answer is kind of key. Okay, so we've now done the RMS, and that is the end of what I had for this.
Wait, so both things that we just did should equal the same thing.
What?
We got the RMS speed.
Yeah.
And that should equal the 3 over 2a. Or no, not that, but the square root of 3. That makes sense. But then you were saying that needs to also to equal to the same thing as what we did up top.
No, what we did in class on, I think it was Friday last week. Was it Friday that I did the kinetic theory of gases? Where I talked about particle bouncing in a box, and we calculated the change in momentum when it bounces, the average time between collisions. So we found the average force was change in momentum on one collision divided by the time between collisions. And we worked our way from there and found that the RMS speed was square root 3kt over m.
Referring to the top of our slides.
No. So this is referring back to what we did in class last week.
Gotcha.
So now we didn't talk about how the Maxwell-Boltzmann distribution was derived, right? Why? Because that takes some higher level statistical work. Thermodynamics is actually called, alternatively, statistical physics. Because thermodynamics is taking a system that is way too complicated to work with each particle and saying, well, let's take statistics to calculate the probability. So, in this room, how many molecules of air do we have in this room? Ballpark number.
6.022 times 10 raised to 23.
That would be what it would be if we had, 22.3 liters? A whole lot more. 22.3, is that right? No, it's got to be smaller than that. It's 22.3 liters.
Yeah, that one. Yeah.
I calculate in this room we probably have somewhere in the ballpark of 10 to the 25th molecules. Yeah, because we're going in the same fashion.
Yeah.
Which what was that?
I said just a few orders of magnitude off.
Yeah, just a few. Well, with his, he was only off by 2 from my estimate. And that's because I'm saying, well, how much volume do we have in this room? And I figure it's about 100 moles in the room. Is that accurate? No, it's ballpark at best. And of course, as I told you in class, that's the fourth root of a googol. Which 10 raised to the 100th power. It was some guy, his kids, and he were playing around. They said there should be a name for a really big number, and so they said 10 to the 100, we're just going to call it googol. And then a googolplex is 10 raised to a
Who
googol.
were these kids?
I like 8 or 10 or something like that.
And they thought that 10 to the 100 should be Google?
Yeah.
When I was a kid, I didn't know what an exponent was.
Blame mom and dad. My niece and nephew knew what a Google was when they were 8.
Oh, I knew what a Google was, but they never said it in exponent form. They're just like, Jeffrey's like, yeah, it's 100 zeros afterwards.
Yeah.
And then a Google Plex is when it has a
Google zeros after.
I've never talked about this till today.
And of course, the Google for the number is spelled different than Google for the search engine, but it's based on,
Yeah, they named that number, right?
Yeah.
You just misspelled it intentionally.
I think so. So coming back to this, even with computers, we can't track, 10 to the 25th particles. And for each one of those particles, you would need to know its momentum in the x direction, in the y direction, in the z direction, and its position, x, y, and z components. You'd have to know 6 things about them, even if they're not rotating, to be able to calculate what's going on. So basically, without any rotation, if they were all monatomic, which in the beginning of class tomorrow we'll talk about what happens when they're not monatomic. If they're all monatomic molecules, they're all diatomic for the most part, because it's 79% nitrogen, that's diatomic. 21% oxygen, that's diatomic, trace amounts of others. So they're all diatomic. You have 6 times the number of molecules of variables you have to keep track of to calculate what's going on. And there's no computer in the world that can do that. And so what the physicists did is they sat down and they simply calculated the probabilities of what could happen. And so we have variables that we call the variables of state. And we have an equation we call the equation of state that relates macroscopic variables to the microscopic behaviors. And so we've talked about one variable of state very clearly, temperature. Temperature is a state variable that relates to the microscopic behavior of the momenta, right? Because it's talking about their kinetic energies. So that's one of the variables of state. The other ones, well, here's the equation of state for an ideal gas, P equals nRT. What are the variables then? The state variables. Temperature is one, pressure, volume, and the number of atoms or the number of moles. R or K are constants, so those aren't state variables. So those are our 4 state variables. And if we know those state variables, of course we don't have to know 3 because we can calculate the 4th from the equation of state. Then we know the macroscopic behavior of the microscopic particles. And so all of thermodynamics is based on that. Which brings up, since I've got a few minutes, I'm going over some key ideas here, which brings up something really important about the second law of thermodynamics. The second law of thermodynamics, we've talked about it in physics class. Do you recall what we said about the second law of thermodynamics?
2 objects in thermal contact will reach
It's relevant to that. I'm not sure exactly which part you're looking at because I used like one law to describe another one. I used the second law to describe the 0th law. So, but you're in the area there. The second law, the statement I said was that heat spontaneously flows from higher temperature to lower temperature. That's one statement of the second law of thermodynamics. Basically, well, I think we all understand that. I let go of my pen, it naturally goes to a lower potential energy state. That's another statement of it. But a third statement, one that people brought up when I first asked them about the second law, I think Ashley might have been the one who said it, was that things naturally go to a higher state of entropy. Well, that brings up the question, what is entropy? Okay, chaos. Now, chaos itself is a very misunderstood term. Chaos means that something is so complicated in its sensitivities to parameters that you can't accurately predict the future. If you knew everything perfectly, you could predict the future, but you don't know everything perfectly, and just a small deviation from knowing the exact value will result in a great difference in the final behavior. Chaos is still governed by the laws of physics. It still has a predictability, And so we actually have ways of dealing with chaotic systems. We say, well, if it's in this state, it's going to go here. And if it's in this state, it's going to go here. It's just, so you have what we call a memory. You can, if you know what it is now, you can figure out what it's going to be this far out in the future. But after that, it diverges and you can't. That's what chaotic is. Okay, so she said chaotic. It is not a bad answer. But the actual answer is really startling in its simplicity. The entropy tells you about how likely the system is. So something with higher entropy is more likely. Something with lower entropy is less likely. So take as an example, I have a deck of cards that are all stacked one on top of each other. And if I take that and I throw them on the table, what's the likelihood they're going to end up all stacked on top of each other? Very low. There's lots of different things they can be. They can spread out all kinds of different situations. And the one situation with them stacked all on top of each other is very low. So that's a very low probability. And having them all spread out, roughly one high across the table is the most likely outcome. And so that's our highest entropy state. That's what entropy really is measuring. We have a mathematical function for it. And that is that entropy, S is the symbol for entropy, is equal to the Boltzmann constant times the natural log of this omega means the number of ways. That's a capital omega. Number of ways the system can be in macro state. And I'm going to end this with one simple thing that we'll use in class. Let's say we have two dice. One a purple die and one a red die. If I roll those dice, what values can I get? Okay, the total. The macro state is going to be the total. Okay, it can go anywhere from 2 to 12. Now, how can I make 2? Okay, 2 would be a 1 and a 1. So how many ways can I make 2? Only one way. So that's one microstate. Now let's just go to, let's go to 3. How many ways can I get 3?
2 and 1, 2 ways.
That's right. 2 and 1 or 1 and 2. So that's 2. For 4, it can be 1 and 3, 2 and 2, or 3 and 1. And so as I go up, the number of microstates increases until when I get to 7, I have 6 microstates. And then it goes back down to only 1 microstate for 12. So this here, this column, is omega, the number of ways you can get there. And so the entropy of throwing a 2 is k times the natural log of 1, or 0. The entropy of throwing a 2 is k times the natural log of 2, and so on. What's the highest entropy roll?
Is it 6?
7, actually.
No, it's at 7, but it's going to be
Yeah,
6.
there's 6 ways, so it'd be k times the natural log of 6.
But out of 11,
11, you can get 2 ways.
5 and 6.
And so if we talk the probabilities, the probability...
I was thinking numbers more than 6 too. So I was thinking 9 and 2, 8
Oh,
and 3.
yeah.
Here's the probability. So like if you go play blackjack, 6 and 36 is the odds of getting a 7. It's blackjack. Craps. If you're playing craps, it's 1 in 6 chance that you're going to get a 7. Opening roll, 7s are good. After that, 7s are bad. Each roll, it's only 1 in 6 chance you get a 7, but it's still the most likely thing to occur. And so, you learn the craps rule, and you learn it's all about statistics, and craps is one of your best chances to actually get a fair return on your money. Everything's biased against you in Vegas, and craps is biased the least. Still hard to get you, though. All right. Have a swell next hour and a half, and I'll see